In this video, we are going to look at IPv4 addressing. We're going to look at an overview of IP addresses, what they look like, and how they function. I'm going to explain the various address classes that you get in IP version 4. In other words, Class A, Class B, Class C, Class D, and Class E. We'll also talk about CIDR and how that changes the address classes. But as a foundation, it's important that you understand the 5 address classes, A, B, C, D, and E. So, what is an IP address? An IP address is a Layer 3 logical address assigned by an administrator. Unlike MAC addresses, which are hard-coded or burnt into network interface cards by the manufacturer, an IP address is configured by an administrator. The IP address may change within a subnet. For example, when using DHCP, or Dynamic Host Configuration Protocol, an IP address resides at Layer 3 in the OSI model. An IP address is used to uniquely identify a device on the network and is used by routers to determine where that device is. So a router routes traffic to a destination IP address based on a hierarchy of network and host, which we'll talk about in a moment. So once again, the IP address uniquely identifies a device in a network, in a similar way to how houses are uniquely identified in a street. Houses in a street have a unique address, so for example, 10 Oxford Street. In the same way, a host in a network has a unique identifier on that network, being its IP address. I'm going to expand on that analogy in the next few minutes. Every device on the Internet has a unique IP address. IP version 4, or Internet Protocol version 4, is a Layer 3 or network layer protocol as per the OSI model. IP version 4 is a connectionless protocol. In other words, there are no sessions formed when traffic is transmitted. The transmitter simply sends data without notification to the receiver. No status information is sent back from the receiver to the transmitter. Each packet is treated independently of other packets. That's why traffic can take different paths to get to a destination. Routers will route the traffic via different paths based on options such as load balancing, because each packet is independent and IP is a connectionless protocol. Routers can also base routing decisions on different values, such as bandwidth or hop count. But it is possible that packets from one session take divergent or different paths to get to a destination. Routing protocols determine the best path or best route from A to B. This is based on the hierarchical addressing structure in IP version 4 and IP version 6, where we have both a network and host portion as part of the address. Routers base their routing decisions on the network portion of the address rather than on the host portion of the address. And I'll explain network and host portions in a moment. IP also only gives best effort delivery of packets. There is no guarantee of packet delivery. Any packet could be misdirected, it could be duplicated, or it could be lost in transmission when sent to a destination. And that should be expected in IP transmissions. So in summary, IP has no built-in sessions, no data recovery, no retransmissions. Higher layer protocols such as TCP will need to handle dropped packets, corrupted packets, misdirected packets, and so forth. IP does not provide those features and relies on higher layer protocols to implement those features. So let's look at the format of an IP version 4 address. An IP version 4 address is 32 bits in size, normally written in dotted decimal notation such as this example, 10.1.1.1. Each value, such as 10, is 8 bits in size. So in other words, we have x.x.x.x with each x being 8 bits in length, also known as an octet. The total size of the address is 32 bits. IP addresses, once again, have a hierarchical structure to enable routing, which consists of 2 main parts. We have the network portion of an address and the host portion. So an IP address consists of 2 main portions. We have the network address portion, also known as the network ID. This identifies a specific network. Routers maintain routing tables that contain network addresses. It's important to realize that routers build their routing tables based on the network address and not on the host address. So they do not route packets from one interface to another interface based on IP addresses. They do their routing based on network addresses. So they will look at the destination IP address in a packet and match that to a network address in their routing table to determine how traffic is routed. So an IP address consists of the network portion as well as the host portion, which is also called the host ID. This identifies a specific endpoint on a network, such as a server, a printer, a PC, an iPhone, an iPad, or some other type of device, including IP phones. These are essentially devices that need to communicate with each other. So PC may be communicating with a server. You may be using your iPad to read the news. So you'll be surfing to CNN.com or USAtoday.com or the BBC. So your iPad is sending traffic to that server, and the server is returning traffic to your iPad. So the iPad and the server will have a TCP session established at layer 4, but for the iPad to communicate with the server, routers need to route traffic to the server and back again. In IPv4, addresses were once divided into 5 main classes: A, B, C, D, and E. These classes help us figure out which part of an address is the network and which part is the host. Class A addresses start with a 0 in the first bit of the first octet, giving us a range from 1 to 126. The first 8 bits are the network portion, and the remaining 24 bits are for hosts. For example, 10.1.2.3 belongs to the 10.0.0 network. Class B starts with 10 in binary and covers 128 to 191. Here, the first 16 bits are the network and the last 16 are the host. Example, 172.16.1.2 is on the 172.16.0.0 network. Class C starts with 110 in binary, range 192 to 223. The first 24 bits, or 3 octets, are the network, leaving only the last 8 bits for hosts. Example, 192.168.1 belongs to the 192.168.10 network. Class D starts with 1110 in binary, range 224 to 239. These aren't for unicast, they're for multicast, sending data from one device to many. Example, OSPF uses addresses like 224.0.0.5. Finally, Class E starts with 1111 in binary, range 240 to 255. They're reserved for research, testing, and special purposes. A subnet mask allows a device to determine, once again, which portion of the address is the host portion and which portion of the address is the network portion. This allows a local PC, as an example, to determine whether the device it wants to communicate with is on a remote network and is thus reachable via the default gateway, or if the device is on the local subnet and therefore does not require the use of a default gateway. So if PC A and PC B are in the same subnet, no default gateway is required. But if they're on different subnets, then a default gateway would typically be required to do the routing between the two PCs. So that's essentially what a network mask does. Now, as I've explained, Class A, B, and C networks have default masks, which are also known as natural masks. In a Class A address, the first octet is the network. In a Class B address, the first 2 octets are network, and with a Class C address, the first 3 octets are the network portion. Before CIDR, we use classful subnet masks, Class A, B, and C networks. A Class A subnet supported about 16 million addresses with a mask of 255.0.0. Class B had around 65,000 with 255.255.0.0. And Class C had just 254 with 255.255.255.0. But here's the problem. What if a company needs 3,000 hosts? A Class B network wastes too many addresses, while multiple Class C networks bloat the routing tables. The solution was CIDR, Classless Inter-Domain Routing. CIDR lets us move beyond strict A, B, and C boundaries. Classful masks were fixed on octet boundaries, /8 for A, /16 for B, and /24 for C. But CIDR lets the mask fall anywhere, not just at octets. For example, 255.224.0.0 equals /11. That means the first 11 bits are network and the rest are host, even though the boundary cuts inside the octet. CIDR gives us variable length subnet masks. It's flexible, efficient, and reduces waste. That's why since 1993, CIDR has replaced Classful Addressing. So remember, Classful Addressing was the start, but today we use CIDR for smarter, scalable subnetting. Congratulations! You've just completed the full journey of IP addressing, from the foundation of Class A, B, C, D, and E, to subnet masks, and finally to CIDR. You now understand how networks identify, divide, and communicate. IP addressing isn't just theory. It's the language that keeps the internet alive. And now you're speaking that language more fluently than ever. So thank you for staying engaged and learning with me. Your curiosity and effort are what turn these concepts into real networking skills. Stay motivated, keep practicing subnetting, and soon you'll master even more advanced topics in computer networks. Once again, thank you, and I'll see you in the next lesson.